So the study of light and matter, again, is spectroscopy. So we'll take a look at this. This is a simple spectrometer. This spectrometer is just shining visible light on the sample.
A spectrophotometer works. A lamp provides the source of light. The beam of light strikes a diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display. Here's how a spectrum...
All right, so this is from your PowerPoint slide here. We have different ones. The continuous spectrum would just be all the colors of the rainbow. And so it's going to look different than something called line spectrum. These are all spectra. Spectra is plural. And so what we do is we'll map out how the light interacts with matter based on the absorption or transmittance of the light. And so we're going to have two types of, actually more than two types. In this one, we're going to look at emission. Okay, so we have absorption / emission spectra. And so a light bulb, if we just take a regular old-fashioned light bulb with tungsten filament in here, what happens is the metal starts getting hot, hot metal. And hot metal, what it does initially is it starts to glow. We can see it here. I can just do a quick demo of this. If I have some matches here. This is stainless steel. Stainless steel is a little bit harder to oxidize. But most metals, you heat them up and they'll start to become oxidized. This one's already been oxidized a little bit. But what's going to happen as I heat up the metal? It starts to glow. Do you see that? It starts to glow red, and then it starts to glow orange. Do you see that? And eventually, if it gets hot enough, do you know what color it glows? White. It's white hot. Have you ever heard the term white hot? Red hot metal? White hot metal. White hot's a lot hotter. And that is, red hot is starting to emit some lower energy light. But once it gets to white hot, white is all the colors of the rainbow combined. It's white light. So that means we're very hot. Eventually, what's going to happen is, even though this is not glowing, I feel it. Do you know what I'm feeling there? Off the metal? I'm feeling heat. The heat's what we call infrared. So that's going to warm up my hand. Infrared's invisible, but I don't want to touch this, even though it doesn't look hot because it's emitting a lot of infrared. It's hot. And so first off, what this is going to start to do is it's going to start emitting infrared, and then it's going to start emitting red, and then orange, and eventually white light. Well, that's what a light bulb does. A light bulb's going to do that. It's going to get white light with it. Now, in spectroscopy, we map out that white light like this. And so we'll just go Roy, G, bid. Red, orange, yellow, green, blue, indigo, violet. And what we're going to see is this light bulb is going to emit a continuous rainbow of colors. Hopefully it doesn't emit much UV. Do you want your light bulb to emit much UV? No, you don't. But, you know, some light bulbs do. Do you know what kind of light bulbs emit a lot of UV? Halogen light bulbs. And so halogen light bulbs, they put a little protector over to block the UV, to shield it. But this is called continuous rainbow of colors. This is a continuous spectrum. All the colors of the rainbow are there. If all the colors of the rainbow are there, we call it white light. And so what does this look like in terms of this, an actual spectrum? And so let's look at light spectra. So this is what we're going to measure. Actually, this is backwards here. This is measuring off wavelength. And so red is over here. Red is actually here. This is infrared here. So red is around 760. And then it goes down to 390. This is UV up here. And so when we look at this, the halogen lamp is this green one, and it's more UV over here, although it's not huge. An incandescent lamp is this tungsten filament. So this is it. And then this is a fluorescent lamp here. The fluorescent lamp looks like white light, but it's not. It's made up of a mixture of different colors. And those different colors add up to white, but it's a little bit different. If we compare this to the solar spectrum is also a continuous spectrum. And so let's take a look at the sun spectrum. This would be an example of the solar spectrum here. The solar spectrum emits, if you look at it, there's a lot of infrared that the sun emits. The infrared's invisible, so you don't see it. And the infrared is at the higher wavelengths. So this is not in terms of energy. If it's in terms of energy, the shorter the wavelength, the higher the energy. And so when I did mine, the red has the longest wavelength, violet has the shortest wavelength. And so if I do a math in terms of wavelength, I just flip it the other way. And so over here at the shorter wavelengths, we have UV. This is UV here. And here's our rainbow. You see red, orange, yellow, green, blue, indigo, violet. So it's going backwards here. But violet's the highest, and then we have ultraviolet. And then red is the lowest, then we have infrared. So this is infrared here. This is the sun spectrum here. You look at the sun spectrum and you compare it to the incandescent lamp spectrum, it's quite similar. And so let's compare the two spectra. So this will be incandescent, solar. Oh, I don't want that. Solar spectrum. Solar spectrum. The spectrum is a measurement of this. So here. And so if we compare the sun's, this is a continuous spectrum too, because it's continuous because all the colors of the rainbow, this is the visible part here, all the colors of the rainbow are shown here. Here's an incandescent light bulb. It's a little different, you know. This is the sun, this is a 3,000 Kelvin light bulb here. A little bit different, but since all the colors of the rainbow are emitted, then it looks like white light. And the same thing with the sun. You can see there's less blue, less violet here in the incandescent light bulb than the sun. The sun's going to have a lot more blue, a lot more violet in there. So what we have here is this. We have a continuous, this is called a continuous emission spectrum. And that's what we're just looking at, continuous emission spectrum. And that's what we get from a light bulb. A light bulb gives us a continuous spectrum. And the continuous spectrum is going to have all the colors of the rainbow. And so what can we make light bulbs out of? Well, we can make light bulbs out of anything that you can excite the electrons in. And so this steel spatula, I can excite the electrons in here. So what's happening? Well, the electrons are becoming excited in the flame. As they're becoming excited in the flame, they start to oscillate. As they start to oscillate, then they'll start emitting light. Well, here, in tungsten, in the light bulb, you heat it by passing electric current through there. The electrons start to oscillate. As electrons start to oscillate, they don't stay oscillating forever. You know, they're higher energy. Eventually, they're going to go back down to lower energy. In that process, they're going to emit light. And so, basically, anything with excitable electrons, we should be able to make a light bulb out of. And so, what somebody tried to do is they tried to make a light bulb out of hydrogen atoms. You know, and it should work. Have you heard of like neon light bulbs? So they'll put neon gas in. Neon gas has electrons, or neon atoms do. And you can excite the electrons in neon. And so what we're going to have here is this. If we try to make a light bulb out of hydrogen, well, that's simple enough. Hydrogen consists of a proton, so this is called a hydrogen lamp. Hydrogen consists of a proton and a single electron. And that single electron, you can excite it to different speeds or different energies, or however we want to think about it. And so, for example, if the electron, one way that people visualize this electron is, some people visualize this electron as orbiting around the nucleus like this. It's orbiting around the nucleus, like a satellite, or like the moon, or Earth. That's what some people think. And so if you give it a little bit more energy, it orbits a little farther. You know? And so higher energy, it orbits a little farther, it's moving a little faster. Lower energy, it orbits a little closer, moving slower. And so if you think about this, that electron should be able to go any speed it wants, right? So for example, this electron should be able to go faster or slower, whatever speed. And so this hydrogen lamp should emit a continuous spectrum. In other words, this hydrogen lamp should emit white light. Right? White light. But people try to do this. It's not that hard to do. It's like making a neon light. You know, you put neon in a tube. Well, you just put hydrogen in a tube. And so we'll look at put hydrogen in a tube. Well, this is what somebody did. They put hydrogen in a tube like this, and then excited it. This is hydrogen on the left. And then they measured the spectrum of this. And what they saw is they didn't see a rainbow of colors. When they excite the electrons in the hydrogen, they only saw 4 colors here in the visible region. And that was it. Just these 4 colors here.
These are unique for every element.
These are unique for every element. Every element shows a different spectrum like this. And so this is not what we call a continuous spectrum. Do you know what we call this? The non-continuous spectrum. Well, the non-continuous spectrum is also called in this case, it's called a line spectrum. Do you see where the origin for line comes from? There are only certain lines of light emitted, and these are discrete lines. That is, they're very unique. In fact, each element has a unique line spectrum. We'll see this over here in this slide back here. Let me just show this one. This is for hydrogen, and hydrogen shows 4 lines in the emission spectrum. It shows a red line here. This red line is very specific. This red line's at 656 nanometers of wavelength. This green line at 486 nanometers, this blue line at 434, and this violet line at 410 nanometers. That's it. Do you see all the other regions are black? It means there's no light being emitted there. And so is this a very good reading light? No, this would be a very bad reading light. These are other, like for example, if we made a light bulb out of nitrogen, out of oxygen, out of mercury, these are the colors that would result. And those colors are totally different because they consist of different lines in the spectrum. So this whole line spectrum was huge. Huge, because this is not what physicists predicted. You know what physicists predicted? A continuous spectrum. They predicted that if you were to excite the electrons in a hydrogen atom, you'd get the same spectrum as you'd get from heating a piece of metal, as heating what we call anything that's a black body, like the sun. You know how the sun generates light? It excites the electrons, and those electrons can get excited to any speed or any energy it wants. And so this was huge because this was not explained by the physics at the time. And so at the time, physics had to be modified. And so the transition from the old physics, which we call classical physics, to the new physics, which we call quantum physics, occurred because of this. Because this is a huge problem. And why is this a huge problem? Because this is saying like this. This is saying like the electron can move at 25 miles an hour, but it cannot move at 25.1 miles an hour. The electron can move at 25 miles an hour, 35 miles an hour, but nothing in between. So how can an electron move at 25 miles an hour, but not 26, 27, 28? It has to jump all the way to 35. And so what this line spectrum is saying is this. The line spectrum says that this energy is allowed. This is allowed. This energy, this speed, this frequency is allowed. This wavelength is allowed, but all these in the black are forbidden. And then this is allowed, this is allowed, this is allowed. So there are only 3 speeds for the electron, 4 speeds for the electron that are allowed. All the other speeds in this range are forbidden. And so what is causing the electron here to only move at these 4 pre-designated speeds? What is holding the electron back from moving at 26 miles an hour? Why does it have to move at 25 miles an hour? This was something that had to be further studied. And so this led to the discovery, the development of new theory, which is quantum theory. Quantum theory is the theory that underlies chemistry. And so quantum theory comes from these observations. What are the observations? The observations of strange light patterns. What are the strange light patterns? It's the line spectra. Line spectra are very strange. We expect continuous spectra. Because the electron should be able to excite to any frequency you want. Low frequency to high frequency. Why is it that the electron can oscillate at this frequency only, and then all other oscillating frequencies are forbidden until it hits this frequency, and then it can oscillate at that frequency? This is like trying to drive a car. Can you drive your car at any speed you want within a certain range, yeah, right? Are there speeds that are forbidden in your car? No, they're forbidden by law, but they aren't forbidden in your car. You should be able to drive from 0 to whatever the maximum speed of your car is, and any speed in between. Right? Does that make sense? So this doesn't make sense. Why is the electron restricted in terms of speed? Right. And so let me talk about this briefly here. So the observation is this: strange light patterns. Strange light pattern. In other words, line spectrum. These strange light patterns led to the forbidden and allowed energies. This forbidden and allowed energies is called quantization of energy. And so it's a little bit different than what we were expecting. So what that means is something like this. In terms of gravitational energy, this is continuous. So we could have any height we want here. And this would be a continuous spectrum of energies. Whereas this would be quantized. We can't have any height because of the steps. So there's certain steps here. And so that means any energy in between the steps is forbidden. And so that's what we got here, forbidden quantization of energies. This led to a hypothesis. The first hypothesis led to something called the Bohr model. The Bohr model turned out to fail, but we'll talk about it briefly. The Bohr model said the electron can only orbit at certain orbits. The first orbit, and then it can't orbit anywhere else other than the second orbit, the n equals 2 orbit. And so the electron can't orbit anywhere. It has to orbit in n equals 1 or orbit in n equals 2, but anything between these is forbidden. So n equals 1.1, forbidden. 1.10, 2, forbidden. And so anything between these is forbidden. And so these are orbits here. That was the first hypothesis. That turned out to be wrong. The next hypothesis was this, which led to the modern day theory, which we call quantum mechanics. Show here, quantum mechanics. And in quantum mechanics, we no longer have orbits. We have something called orbitals. So let's talk about it. There are some additional developments. And so Bohr model had orbits. Quantum mechanics has orbitals. It sounds similar, but what we have to add here is we have to add one more thing, and that's the wave-particle duality of matter and light. And one other thing. We have the wave-particle duality, and we have something called Heisenberg uncertainty principle. Since this is too much for Chem 4, how they organized it is a little weird. We'll just leave it. And so these are some key words here. Line spectrum, discrete lines, wave-particle duality. Wave-particle duality of matter and light. Light, we have something called the photon. The photon can be thought of as a particle of light. And matter is a little bit different. Matter will have a wavelength. I guess we're out of time. We'll continue this.